Hi everyone, in this video we are going to practice taking two half reactions, balancing them, and then bringing them together to actually figure out what the total equation is going to be. But we're going to do this in the context of galvanic cells. So the most important thing you can do here is first balance each half reaction, then identify is it an oxidation or reduction reaction. Using that information you will then be able to figure out was that at the anode or the cathode, and then after you have all of that you can add it all together and figure out exactly what the total equation is for the entire galvanic cell or this entire battery. So let's just do this example by example. There's only 3 problems in this video, so just take your time and work through this. Here's the first one. So you have 2 different half reactions. I want to know which is the anode, which is the cathode, and then once everything is balanced, then I want you to add it together and tell me what the net reaction is for this galvanic cell. Go. All right, did you get an answer? Hopefully you did, but if you didn't, do not get frustrated. This is definitely something that takes a little bit of time to master. And so maybe we'll work through this first one together and then you'll be able to do the second and third one on your own. But the first thing you absolutely have to do when you try to determine your net chemical equation or your net reaction for a galvanic cell is you need to assign oxidation states. So always start with oxygen if you can. So let's start with this first half reaction by assigning oxidation states. So I'm going to start with the MnO2 here. So I see that we have oxygen. Oxygen is always going to have a -2 oxidation state. There's 2 atoms, so we multiply them together, so you end up with a -4 for oxygen. Now we know that this overall compound is neutral, and so it needs to have an overall charge of 0. So the only charge or oxidation state that manganese can have must be +4. So +4 -4 definitely gives us 0, so that's good to go. Water, we've done this a ton of times. We know that oxygen is -2, which means that water must be +1 because there's 2 atoms, so +1 times 2 gives us a +2 overall, -2 gives us 0 for the overall charge for the compound. Then we move on to Mn2O3. So this one's more complicated. So oxygen is definitely going to be a -2 oxidation state, but there's 3 different atoms. So -2 times 3 gives us -6 overall. Now this is a neutral compound, so our something -6 has to give us 0. So our manganese overall needs to have a +6 charge. But there's 2 atoms, so we take the +6, divide it by 2, and we end up with a +3 oxidation state for each of the manganese atoms. All right, and then the last thing we need to do is to identify the oxidation states of our hydroxide ion. We know that oxygen is -2. We know that hydrogen is +1. -2 + 1 gives us an overall charge of -1, so we're in good shape. Let's go ahead and just assign our oxidation states of our second half reaction as well, since we're already in this mentality. So zinc is by itself, it's in standard state. Whenever you see something, an element that's sitting by itself, you can automatically assume that it's going to have an oxidation state of 0. When we have our hydroxide ion, we just assigned these charges in the previous half reaction, so I'm just going to take our -2 and +1, nothing has changed. Now let's look at our zinc hydroxide compound. So we know, if you already know, that OH- always has a -1 charge, so in theory you could do it that way and just use the -1 for the whole thing, but let's do it from the very simplistic standpoint. So we know that oxygen has a -2 charge, and then we know that hydrogen has a +1 charge. So -2 + 1 gives us an overall charge of -1. But for our hydroxide polyatomic ion, there are 2 of them, so there's 2 hydroxides. So -1 times 2 actually gives us an overall charge of -2, meaning for our overall compound, in order for it to be neutral, our zinc must have a +2 oxidation state. So +2 -2 gives us 0. All right, so now we've properly assigned our oxidation states for every single compound in both of these half reactions. Now what we need to do is figure out how many electrons there are, or figure out where we need to add electrons to which side. So you go through each one of these. Let's start by looking at this first half reaction on the very top, and you look at each one and see what has changed, and automatically look for those weirdo oxidation or weirdo symbols, weirdo numbers, whatever kind of sticks out as odd. And so for me, I automatically look at manganese and go, okay, it went from +4 to +3. We definitely need to have our oxygen or our charges balanced here. So from +4 to +3, you always start with a more positive side. We need to add electrons to the side. So we need to add 1 electron for every single manganese, but we can see on each side of this that we actually have 2 manganese total. So instead of adding 1 electron, we absolutely have to add 2 electrons in order to balance out the charges for both manganese species. All right, so now we've added 2 electrons to this half reaction. They are on our reactant side or our left side, meaning this is definitely a reduction reaction, meaning this is the reaction that in a galvanic cell definitely takes place at the cathode. Okay, so that's our first step. Now let's go to our second half reaction. And so what we see here is that our zinc, remember, look for our weirdo elements, the ones that aren't oxygen and are not hydrogen. And so we see zinc, we see that it goes from a 0 charge to +2. So the +2 is definitely the more positive side, so we're going to add electrons to the side. We know that there's a difference of 2 electrons here, 0 going to +2. We definitely have a difference of 2 electrons. There's only 1 of each atom, so we just have to add 2 electrons. We see that these electrons are now on the right side, they're on the product side, so this definitely indicates that we have an oxidation reaction. This definitely occurs at the anode. All right, not done yet. We've identified the half reactions, we've balanced our half reactions, we figure out what they are, now we just have to add them together. But in order to do this, you have to check and make sure that your electrons on each side have the exact same number. And we're lucky here, they're both 2. So boom, that cancels out, and then boom, this one cancels out. Look, is there anything else that repeats? We only have 1 water, that doesn't repeat, but oops, here we go. We see 2 hydroxides on this side and 2 hydroxides on that side. So those 2 are definitely going to cancel out. Everything else is unique, so we just bring it down. Add it all together. So we end up with 2 MnO2 plus zinc plus water goes to Mn2O3 plus zinc hydroxide. And then just check and make sure everything looks natural. You want to make sure that this bottom reaction is balanced. If it's not balanced, then you know you've made a mistake somewhere. But definitely this is the correct answer. All right, so let's try another one. Also challenging, but let's see how we can do here. All right, go. I want to know your anode, your cathode, and your net reaction. Go. All right, did you get an answer? Hopefully you did. I'm going to move through this one a little bit faster this time because we should already be very familiar with some of these oxidation states. So for example, we always know that water is +1 for hydrogen, -2 for oxygen. We solved in our previous example, we know that our hydroxide is -2 + 1 with an overall charge of -1, so we can apply that here as well. And now we can go through and start applying oxidation states for everything else. So like we said before, we know our hydroxide overall is a -1 charge, so I'm just going to assign that for the whole OH part, okay? So this is -1. We know that our oxygen is always -2 here, so we have a -2 plus a -1. Overall, this compound is neutral, so -2 plus -1 plus something else has to be equal to 0. The only way we can make this mathematically balanced is if we give nickel a +3 charge. All right, so that one's balanced. Our water's balanced. Let's move on to our nickel hydroxide. Like I said before, we already know our hydroxide is a -1 charge overall, so -1 times 2 gives us a -2 overall. In order to balance this out for a neutral compound, our nickel must be +2. So +2 minus 2 definitely gives us 0. That's balanced. All right, let's move on to our second half reaction. We see cadmium sitting here in its standard state. It's definitely a neutral compound, so it's an oxidation state of 0. We already balanced our hydroxide. Let's do our last one here. So our hydroxide we said we know is a -1 overall. There's 2 polyatomic ions there, so we have a -2 charge. This is a neutral compound overall, so +2 minus 2 definitely gives us 0. So hopefully that wasn't too fast. Hopefully it wasn't. But if it was, just pause for a second and go through each one on your own and make sure that all sinks in. So now what we have to do is start balancing our electrons. So again, look for our weirdo elements, so our ones that are not oxygen and hydrogen. So if we look at our first example, the only thing that's weird or not oxygen and hydrogen is nickel. And what we see is that it goes from +3 in the reactant state to +2 in the product state. So again, we always start with a side that is the more positive. We see that we've gone from +3 to +2, so we have a difference of 1 electron, but then we need to check. We see that we have 2 atoms on each side. There's 2 nickels. So each nickel has been changed by 1 electron, so we actually need to have 2 electrons overall for this half reaction. And so we need to put a 2 right here. Now, we see that we've added electrons to the left side, our reactant side. This is definitely a reduction reaction. This definitely occurs at the cathode. All right, let's look at our second half reaction. Now again, we're looking for our unusual element, so something that is not oxygen and hydrogen. So my eye is immediately drawn to cadmium. So now I see that we go from cadmium 0 on the left side, the reactant side, to cadmium +2 on the product side, okay, so our right side. We see that our product side, our cadmium +2, is our more positive side, so we're going to be adding our electrons to this side. We can see that we have a difference of 2 electrons. It went from 0 to +2. The only way that's possible is if we added 2 electrons electrons to that product side in order to balance this. So we see that our electrons are on the product side, it's on the right side, it definitely has to be an oxidation reaction, which means this is the reaction that definitely is occurring at the anode. Alright, so we've done the first half of the problem, we've assigned the oxidation states, we've balanced our equations, we've identified which is oxidation reduction, cathode and anode. Now we have the very, very last step, and we try to bring both pieces together to figure out the overall reaction that occurs at this galvanic cell, or in the overall electrochemical cell. Alright, so now, last thing we need to do is balance things out. Or do our electrons balance? Yes, they absolutely do. We have 2 electrons here, 2 electrons here. We can cancel those out. That's beautiful. We also can see, just like in the previous problem, we have 2 hydroxides, one on each side. Okay, one reactant side, one product side. But that looks like that's it. Everything else seems unique. And so all you have to do is bring it down to end up with your total net chemical equation, or chemical reaction that occurs in the galvanic cell. So in order to do this, you just bring it all down. So 2 NiOOH plus your cadmium plus 2 waters goes to 2 NiOH2 plus cadmium hydroxide. Boom. And then always check your last reaction, make sure everything's balanced. If it's balanced, then you know this, you've done this properly. One question I always get, hey, Dr. B, I put these in a different order. I said cadmium plus nickel plus water, or I said water plus cadmium plus nickel. Does it matter? No, absolutely not. The only thing that matters is that every reactant stays on the reactant side and every product stays on the product side. So if you had somehow come up with something where you put this piece right here, a product, you had switched it over to the reactant side, that would be incorrect. But as long as you keep it on that right side and on the product side, then you are golden. All right, let's do one more together here. This would be our car battery, or our lead acid battery. So let's work through this one and just take a second, but do the same thing. I want to know anode, cathode, and net reaction. Go. All right, did you get an answer? Hopefully you did. This is our last one, so I'm really hoping and praying that this was something you just flew through and you feel really confident about yourself and your skills right now when doing oxidation and reduction half reactions and balancing them specifically. All right, so let's go through the steps. It looks like it's all balanced, so all we need to do now is identify oxidation states. So let's start with this first half reaction. What I see here is I have lead by itself in its standard state. It definitely is going to be neutral overall, so it's 0 for its oxidation state. Now we move to the sulfate anion. So we know it has a -2 charge overall. We have to take that into consideration. Let's start with the oxygen. Oxygen is -2, but there's 4 of them, so -2 times 4 gives us -8 overall. We know that whatever the charge is for sulfur, -8 has to give us an overall charge of -2. So we still want to say the negative. This value only can be +6. So 6 minus 8 definitely gives us -2. We've balanced that out. Now, we know that the sulfate polyatomic ion always is going to have a -2 charge. So anytime you see SO4, you can just say -2. You know that overall component's going to be -2. If you don't like that, you can do it this way, but it's just a waste of time if you know what the overall charge is. So sulfate is -2, meaning that this lead component has to be +2. It's an overall compound as neutral, and so +2 minus 2 definitely gives us 0. All right, so let's go down to the bottom here. Let's start with lead oxide. We know oxygen has to be -2. There's 2 atoms, so -2 times 2 gives us -4 overall. It's a neutral compound, so something -4 needs to be 0. The only thing that could be mathematically in order for it to be true has to be that lead has a +4. All right, let's move to hydrogen. We did this one in a previous video. If it has a plus, then you know that's the charge. Very simple, +1. Sulfate, we've already done this one. We know that our sulfur is +6 and our oxygen's -2, but there's 4 overall, so it gives us -8. Lead sulfate, we just solved for this one. +2 for lead, overall for sulfates -2. Water we've done before, +1 -2. So hopefully I'm not going too fast. If not, look at previous videos to figure out exactly how we do oxidation states. All right, here we go. Let's look at this first half reaction. Now we need to balance it in terms of our electrons specifically. So, look at your atoms that are not oxygen and hydrogen. So our only 2 options are sulfur and lead. Right away, what I see is that lead goes from 0 to +2. This is something we need to balance its charge. Now we see that on the product side, it's our more positive side, so we definitely have to add our electrons to this side. But what we see here is that it goes from 0 to 2, so it's not 1 electron difference, it's a 2 electron difference. Now we see our electrons are definitely on the product side. This is definitely an oxidation reaction, meaning that this is the reaction that occurs at the anode. Now, Excuse me, now let's look at our second half reaction. Again, we're looking at not our hydrogens, not our oxygens. So we can either look at sulfur here or lead. But my eye is right to lead again. I see that it goes from a +4 to a +2. So that's definitely something that's not balanced. We need to balance our equation. And so we have our lead. +4 is on the reactant side. So that's our more positive number. So we need to add electrons to that sign. So we're going to add electrons here. We see that it's a difference of 2 electrons. So it goes from +4 to +2. The only way we can balance this properly is by adding 2 negatives to this in order to balance it out. All right, so now we see that everything's balanced. We see that we've added our electrons to the left side, our reactant side. This is definitely a reduction reaction, so that has to take place at the cathode. Whew, okay, we're almost done. So we've identified our oxidation numbers. We've figured out what is an oxidation and a reduction half reaction. We figured out where this takes place in the electrochemical cell. The very, very, very last step is we need to add them together and figure out what our total reaction is in that galvanic cell, or what our written chemical equation is. All right, so we have to balance out electrons first. We were lucky here. They're both 2. Just cancel them right out. I can't find my pen. There we go. Cancel them both right out. And so then we can look at everything else. Does anything else cancel? I personally don't see that anything else cancels. The sulfates are on the same side. The lead sulfate are on the same side, so we can't cancel this out at all. So we bring everything else down. So we have our lead oxide plus our 4 hydrogens plus our SO4 2-, but there's 2 of those, so we have to do +2, plus our lead. Keep going. We have 2 lead sulfates plus 2 waters. This is a totally acceptable finished project, but most people actually put the H plus and the SO4 together. So most people write this out as 2H2SO4. Would I expect you to know that? No. But would I expect you to look at this and say, oh yeah, that makes sense, that we could take 4 hydrogens and 2 sulfate anions, put them together and end up with 2 sulfuric acid molecules? Yes, I would expect for you to be able to do that. So hopefully this makes sense. This was kind of a long-winded video, but I really wanted to give you some more examples of this. I know this is some of the most challenging material in this unit, but good luck. Take care of yourself. Practice, and drink water.